Thank you, Prof. Welcome.
Thank you.
Let me start by introducing Professor Maaza. Professor Maaza is a native of North Africa. I think Algeria, to be specific. Prof, you'll correct me if I'm wrong. He holds a PhD from the University of Paris 6, and he's a current incumbent in South Africa of the UNESCO, UNISA, Timberlabs and RF Africa Chair in Nanosciences. He's a joint staff of the University of South Africa, as well as the National Research Foundation of South Africa, Timberlabs, I think. He's a fellow of various academies, including the African Academy of Science, the European Academy of Arts and Sciences, as well as the National Academy of Science of India, and the Islamic Academy of Sciences, the Royal Society of Chemistry, and so forth. Professor Maaza has been bestowed with several awards and accolades, including the African Union Kwame Nkrumah Award for Excellence in Science and Technology, the Galileo Galilei Award, I hope I'm saying that right, by the International Commission for Optics. So welcome, Maaza. We look forward to your talk, which is entitled Nanosciences and Nanotechnology from SDGs to Society. Over to you, Prof. Maaza.
Thank you, Program Director. Senior and junior colleagues, allow me first to express my gratitude to the organizers, and in particular Prof. Nosipo Moloto, for their kind invitation in associating us within this endeavor. My contribution, as was mentioned by Program Director, is Nanosciences and Nanotechnologies from Sustainable Development Goals to Society. In fact, this contribution is given within the framework of the UNESCO, of the Nanoscience African Network, and the UNESCO UNISA Africa Chair in Nanosciences and Nanotechnology. The outline that I would like to follow, but I can say I will not go deep to the science. I would just share with you some of the outputs that we have managed to achieve within this framework of these two continental platforms related to water, related to nanofertilizers for agriculture, related to energy in terms of smart windows and green air conditioning. And in particular, at the end, I would like to close with the case of CO2 capture, sequestration, and valorization to products of an interest from industrial point of view. The NanoAfnet is a network of a network of excellence of the African Union since 2005, and which was created in 2005 in Italy, in Trieste, and have been bestowed that moral support as well as financial support in 2010 by the African Union in Addis Ababa. And the UNESCO chair is, of course, a UNESCO endorsed platform. While the NanoAfnet is headquartered and administered from Timberlabs in the Western Cape, the UNESCO UNISA Africa Chair in Nanosciences and Nanotechnology is headquartered and administered at UNISA main campus in Pretoria. Since the inception of the NanoAfnet, there were 3 pillars which have been identified. The first one is implement a nano human capital development, training PhDs and MScs from all over the African continent in the field of nanosciences and nanotechnology, and in parallel to that, create and initiate and implement a human capital mobility program for emerging young scientists and senior scientists. And these programs, the 1 and 2, were operational since 2005. Then it was targeted that we should create a second leg, which consists of 2 major components: create a an African Nanoscience Master Program, and also create an open access nano journal from Africa with hopefully a high impact factor. And it was decided in 2005 that 20 years, in 20 years time, we need to come with not only knowledge generation, but to groom a new side, a new kind of, and a new profile of youngsters in particular, to have them acquiring entrepreneurial capabilities, and therefore embark in nano innovation and patenting, as well as spin-off companies. And that program has started this year in effect. While program 1 and 2 have started, as I mentioned, in 2005, non-stop, and we have trained a large cohort of African fellows from all over the African continent, including war zones. In that time, that was Rwanda and Libya after that, and as well as the DRC, but non-stop. And we have a cohort of around 52 approximately per year, 52 fellows, PhD, MSCs, PhD, and postdocs, as well as emerging young scientists and senior scientists. If I may single this fellow here, she is from Sudan, from Eritrea, from Cameroon, from Morocco, from South Africa, from India, from Ghana, South Africa, Madagascar, and Uganda, to name some. And colleagues, the gender aspect, in view of the SDGs, we obey by it. 50% of the fellows are females and 50% of them are males. And as you, how can I say, you would have guessed, because it's a UNESCO chair, therefore our research activities are geared towards SDGs automatically. Well, and of course, we cannot target all the SDGs, but we have focused on some of them. And that is zero hunger, SDG 2, SDG 3, 4, 5, 6, 7, and of course 17 and 13, as you would see. So I will go through different typical examples to share with you how we have managed to do it. In effect, alone we would have never been able to do it, but conjugating the efforts and different systems of education from different parts of the continent, being it Lusophone from Angola, being it Francophone from North of Africa and West of Africa, and Anglophone from the rest of the continent, we have managed to conjugate our efforts and come with the potential solution and duplication of this program in these different parts of the continent. In terms of SDG 3, it is established, colleagues, that it is established that we have a fantastic pool of indigenous knowledge. So we embarked in this regard, colleagues, to try to find out how we can benefit from indigenous knowledge and to give it a scientific to validate it scientifically and to apply it. And in this, how can I say, in this, colleagues, dynamic, there is always in each of these focus areas or projects, we involve postdocs, MSCs, and PhDs, as you can see, and Tombi from South Africa, Nandipa from South Africa, Hamza from Egypt, and our colleague Razi Murad from Iran, from the South, the global South. And colleagues, one of the major, I have no clue why it has not showed here, but in one of the major problems in Africa, colleagues, is the skin melanoma cancer, and that is related to the high DNA in the southern hemisphere in particular, and therefore we embarked to find out if one could find a benefit from indigenous knowledge and find a cure for it, a cost-effective cure for it. And it happened that the Khoisan, which is a community within the Southern Africa, do use what we call Hoodia gordoni, and they use this Hoodia gordoni to chew it to remove a fat from their body. And in effect, it was found that this complex here, which is called now P57, is the active phytocompound, and we have used it. And it happened that also the Khoisan community, they use this powder, the powdered version of this plant to put on their skin. And it happens that this Khoisan has the least cancer melanoma. So we thought that maybe let's conjugate this powder and use it to biosynthesize or bioengineer cerium oxide. And it has, as you can see, colleagues, this paper has appeared in Nature Scientific Report. This material has a high blocking efficiency in the UVA, UVB, UVC, and you can compare it, colleagues, to what is happening, what is available in the market. So it can see that nanoparticles synthesized by this method have such a huge blocking capacity over a huge, large blue UV spectral range. And colleagues, as you can see here, indeed, this is the reflection, the reflectivity versus the wavelength. You see here in the blue UV and here in the near infrared. Colleagues, you would see that clearly here we are at the background that we cannot even, the detector can even, it's the limited detection. So it's a really nearly zero, and it has a heavy side profile relatively to classical cosmetics to protect against the UV. And what is better than that, colleagues, is that this cerium oxide, not only it blocks the UV, but as you can see, the ROS, its ROS production is extremely low relatively to the standard one that we use, the TiO2. You see the ROS is extremely low. That means these nanoparticles biosynthesized with using the Hoodia gordoni are less harmful to the DNA. The ROS is nearly zero, colleagues, relatively to the TiO2, and see at a high concentration. The other example, colleagues, that we have investigated also, which has appeared in Nature Scientific Report, is the red ochre that the Himba people do use to protect their bodies. In effect, the Himba people is a black community which lives in the north of Namibia and in the south of Angola. They do not shower, and they are not, how can I say, they are rarely sick due to bacterial infections. But they have not registered a huge amount of bacterial infection related. And this Himba, they coat their body with this red ochre. And we have found out that, and also they are a community which has the least cancer melanoma skin cancer. And therefore, what we have done, we investigated this red ochre that they use, and we found that it is nanometric, and it is iron oxide, but nanometric. And what also have found that, as you can see, colleagues, the UV is not, it's not 100% UV blocking, but the UV are blocked at nearly 95%, colleagues. And what happened that, and this explains why their, how can I say, skin melanoma cancer is very low among the communities living in the Southern Africa. And in addition to that, colleagues, not only it protects them from UV radiation from the sun, but the reflectivity of this red ochre, the diffuse reflectivity of this red ochre is above 50%. That means the infrared from the sun or the heat from the sun are reflected back, diffused back. That means that it protects them from skin burn there, and therefore not only it protects them from the UV radiation, but from the heat from the sun also. And it was found that from antibacterial point of view, this iron oxide that they mix with the goat milk to make a formulation that they put on their body, all over parts of their body, it protects them against the E. coli and the Staphylococcus aureus, because as you can see here, this is the how can I say, the inhibition zone due to this serum oxide bioengineered using Hodia and compared and its effectiveness against E. coli in black and Staphylococcus aureus in red at different concentration. And colleagues, do you see here, for example, this is the standard streptomycin that is used against this bacteria. Yes, it is not high, but it is effective. It is not negligent. It is effective. While streptomycin is $17 small tube, here you would imagine that this red ochre in goat milk formulation is certainly cost effective and can be made in an indigenous way. So colleagues, this was just two typical examples related to health application, but using indigenous knowledge, validating it scientifically. The second, and of course, colleagues, we are very active in terms of drug design from a computational science point of view. We have a really very good team in that regard. If I may come to how can I say, SDG 2, which is to minimize or to ensure food security within the African continent, and in particular, sustainable farming. In this case, colleagues, you would, how can I say, all of us, we are facing this increase of food cost increase all over the African continent, and in fact, all over the world. That is due mainly to the conflict in Russia and Ukraine, because both of them are the major producer of fertilizers. Whatever is related to nitrogen, it's dominated by Russia, and the other two major components, it's dominated by Ukraine. So therefore, the price of fertilizers has rocketed extensively, and therefore it is necessary for us to come with a local solution and to address it. And it happened that Nanosciences can assist in that regard, and I would like to share with you. I'm sharing, colleagues, with you this plant here, which is called the doom. It's Thebaica hypaine. It's a type of palm that mainly you can find it in Egypt and Sudan, as well as Saudi Arabia and Yemen. But equivalent of it does exist in Kenya and Tanzania. Again, colleagues, for this project related to the possibility to synthesize nanofertilizers, again, we involve PhDs, a group of fellows, PhDs and MScs from Botswana, from DRC, Egypt, and South Africa. And the colleagues, the idea is not to come with organic fertilizers, no. And we are not feeding the how can I say, the soil. We have to feed the plant itself. And this is the most expensive one. And how can I, this which is imported from overseas. So colleagues, we have attacked this involving agri-expert or agri-fellows who are carrying out agri-PhDs, as well as life sciences and chemists and physicists. And in that regard, colleagues, it is expected that in terms of food shortage by continent, Africa would suffer most. Yet Africa has the largest arable land, and it is expected that we would be the ones who will be suffering of that, and also the South. The reason is that the fertilizers, colleagues, as you can see, this is the consumption of fertilizers by continent and by region since 1961 up to 2014. As you can see, the bulk of the part of it is Asia due to its population, then North of America in pink here, and in peach, sorry, then in blue, that is in Europe, then how can I say, South America in brown, and in a violet but extremely thin line, a thin line, that is Africa, and the rest, the Caribbean and Oceania. You would see, colleagues, that the consumption of fertilizers from the African perspective, yes, it is increasing like everybody, but it's extremely very low, very low. Why? Because the cost of it, which is extremely very high. So, colleagues, as I mentioned, the nitrogen fertilizers is dominated by Russia. The potash is and somehow phosphate by Ukraine, and phosphate by Belarus and Morocco, and therefore it was necessary for us as scientists. It's a moral obligation to come with a potential solution, and particularly from the physics point of view, but from the nanoscience point of view in particular. So, colleagues, I will not go through the details. I would not share the details of the fabrication, but what I can assure you, colleagues, we have managed to produce and nanosynthesize in a reproductive way a nano-scaled calcium carbonate. You are aware that calcium is a necessary nutrient for a plant, but the nano aspect of it is extremely important, because at the nanoscale, the nanofertilizer can, and the nanoparticle can diffuse easily in the cell, through the cell wall and through the roots and so on and so on, and it can be sucked up to the plant, to the top plant, top region of the plant, and so on and so on. So we have, colleagues, succeeded to produce at the laboratory scale a nanoscaled calcium carbonate, but with a high shape anisotropy. And, colleagues, here is the test by the agri colleagues. This plant here, the first one here, it's without it's the control one, without any fertilizer. The second one with the fertilizer, the third, and so on and so on, a high, and we increase the concentration to see what is the threshold of the toxicity for the plant. But, colleagues, here, just simply wise, here is the plant, the tomato, the plant which gave the tomato without as a control, without fertilizer. This one with the smallest concentration, or this one with a higher concentration, and this is with a larger concentration. And if we go above this concentration, the fertilizer becomes toxic to the plant, and therefore, and the test wise, it is the same. So you do see, colleagues, that these nano fertilizers do indeed have an impact and can be produced in the lab, but certainly now we have to go to TRL 4 or 5 to produce in a mass. But nonetheless, it is demonstrated that we can produce these nanofertilizers in Africa. And we will be sharing this know-how once the patent comes out. We will be sharing this know-how with all the fellows, and therefore they can produce this locally to the local farmers, not in a mass scale, but to the local farmers, to obey by the protection rules and so on. Here, I would like to just to express my deep recognition to the previous speaker who really paved the way for it. Also, we are involved in SDG 6 in terms of water. And again, here, we put massive efforts in that regard, involving a fellow from Senegal, South Africa, Egypt, Iran, and Iran from computational point of view. And that was necessary because we have found out that if from computational point of view, if you create defects, you make the TiO2 more active and active in other parts of the solar spectral range. And in that regard, colleagues, you are aware that Africa will really face, according to the expectations or the projection of the United Nations and the number of international organizations in the field of water, as you can see, a number of African countries will be under vulnerability or stress and even scarcity. Many of them will be under scarcity, as you can see, colleagues. So here, including, for example, the case of South Africa and Egypt, and Somalia, Malawi, Rwanda, Burundi, Kenya, Cape Verde, and Djibouti. But a number of them will be also under stress. It is as dangerous as the scarcity one. And therefore, you can see clearly, colleagues, all African countries, except some who have huge underground water reserves, would face vulnerability, will be under vulnerability level. And therefore, we need to retreat the water that is used. And for such a photocatalyst, as it was mentioned, are the ideal. We embarked in the TiO2, colleagues, because it is multifunctional. And we have managed, colleagues, the idea is to try to create defects in the TiO2 to create some energy levels here, which would make the TiO2 active in the visible without doping, either in the visible or in the infrared. And colleagues, in that regard, let me show you. Here is the TiO2 synthesized via bioengineering, which means that we use natural extract, only natural extract, and water as a solvent, and the titanium precursor to make the titania. And this reaction takes place at room temperature to produce this material, this bulk, as you can see that we call a bulk. It's a black TiO2. And to create that black TiO2, it was easy because the computational show that if we create defects, selective defects on the surface of the TiO2 is no more white or yellow, but black. And that was observed experimentally, colleagues, published 10 years ago by the group of Shan in the US. And they have made that black TiO2 by heating it under hydrogen at around 600 degrees Celsius. But in our case, we always force the destiny in a way to say that Africa is rich in terms of fauna and flora. In particular, we have a high world expert in phytochemistry. Therefore, how can we use natural extract as an oxidoreduction systems? And here, colleagues, please allow us until the patent will come out, and we will share with you the methodology. And as you can see, colleagues, if we anneal this powder at different temperatures, it changes color, and of course, it becomes whitish and yellowish at the end. Colleagues, this, how can I say, investigating this TiO2 shows clearly that is, in particular, I would stress, and colleagues, I will only stress on this sample here because it's the one which has showed the highest response from photocatalytic point of view. it has, can I say, of course, it is contaminated by some potassium, sodium, and magnesium. These are contaminants coming from the natural extract, while here it is nearly anatase, but highly defective anatase under huge pressure and so on. And when we do the ESR, colleagues, we see clearly a signal here, which is a sign of defective sites, and in particular, it shows that it is this signature links to the TI3 plus. Sorry. And when we do, colleagues, modeling, modeling, we find out that if we go for some specific sites, indeed, if we create some defects in some specific sites, indeed, we move from a large band gap to nearly non-existing band gap at all. So, or low value, low band gap, low energy band gap. That means, and here this is confirmed somehow, these are the black TiO2, which exhibit a high absorption in the visible near infrared, and while when you heat them above 450, it gives us a diffuse reflectance equivalent of that anatase and the rutile. But this is the blue area here is that is the related to TiO2 defective. And if it is that, how can it be active? Because it absorbs a lot. It absorbs extensively light. It's like the copper oxide. But here it's TiO2, a black one, which is oxygen defective. And colleagues, here is the standard methylene blue. This is the methylene blue plus water without the black TiO2. This is with the TiO2 dispersed in it, but exposed for 30 minutes. And this one, the same thing after 120 minutes. But colleagues, I would like to stress on the fact that to push the agenda far and to show that because it absorbs until the near infrared. So what we have done, we have covered these tubes with the aluminum foil in each of the at each stage. What does it mean? That means we wanted to ensure to block any light coming from the surrounding and to see if this TiO2, black as it is, if it is effective in dark. Colleagues, this is exactly what happens. Here is initially, and here is with the methylene blue at 30 minutes in dark, without exposure to any external light. And well, there are two possibilities. Either there is indeed a chemical reaction, and how can I say, this TiO2 changes to another form, less defective, and how can I say, and that reaction makes it in a way that the methylene blue is reduced, is decomposed. And this other solution is that this methylene, this TiO2 is active to infrared, but these infrared do come from where? Well, colleagues, the experiments are run at 25 degrees Celsius, and the water has an emissivity. The water within which, the liquid within which the TiO2 is dispersed has an emissivity, and the glass, plastic as it is at room temperature, 25. It has another emissivities, and even we are coating with the aluminum. In effect, the aluminum has an emissivity, and how can I say, these material which do possess an emissivity do emit radiation, infrared radiation, by through the law, Stefan's law, epsilon sigma T power 4, and therefore unless these materials are cooled down, they will not emit a lot. but it is not the case, colleagues. Here they do emit, and we do believe that this activity is due to the infrared emitted by the water containing the CO2, the plastic container, as well as the aluminum sheet. And colleagues, here is the standard curve of the log of the absorption, relatively normalized one. And as you can see at 100, 120, it is quite, it decomposes. It's very active. And hopefully with this, the patent will come soon. We will share with you, colleagues, and I am sure that you will be able to reproduce it in your own labs, respectively. The other example that I would like to share with you, colleagues, is
I'm giving a minute to wrap up, please.
Sorry, Prof. Moloto?
You have a minute to wrap up.
Ah, okay. So I think I should, therefore, I cannot go through it. Let me jump, please, to the other one, to the last one. Colleagues, you have seen before I showed with you and shared with you, colleagues, the possibility of engineering the calcium carbonate for fertilizers. In effect, generating the calcium carbonate for fertilizers or for other application, we use it by catching the CO2 and transforming that CO2 via green bioengineered process to calcium carbonate or to any carbonate. But we do it at room temperature, colleagues, and with water as a universal solvent, and catch the reaction has 100%. And colleagues, we do it because how can I say, colleagues, South Africa and the north of Africa, South Africa is the major CO2 emitter in the African continent, as well as the 11th emitter of CO2 polluter in the world. So from that perspective, we embarked in how can I say, carbon sequestration and valorization. Well, colleagues, we do not, due to limitation of time, I will not go through the details, but using a biophysical chemical approach, it is possible to convert the CO2 to a multifunctional product that can be used as a white pigment, as a fertilizer, or as a component in the cement industry. And that is, colleagues, related to what I showed you before. Just, colleagues, before, how can I say, ending this presentation, I would like just to, program director, if you allow me, just to how can I say, share this last slide. Colleagues, we have managed with the Royal Society UK and with the Science Open International Germany and with UNISA Publishing House to create Nano Horizon, which is an African driven nano journal involving our colleagues from the South. And we have started to publish, where it's extremely highly selective. Why? Because we are intending to have an impact factor of 10 by 2028, and therefore we are extremely very selective. But you are more welcome, colleagues, to submit your publication to this journal, and by the end of this year, hopefully, we will have it DHET approved by our Ministry of Science and Technology and High Education. And thank you, Prof. Moloto and colleagues. Thank you so much.